Right. So in the last class, we looked at these gradient-based methods, right? So we looked at two classes of algorithms. One was the gradient descent algorithm. But in general, we were always looking at these descent-based approaches, which are iterative algorithms, wherein the value of x at time t plus 1 is equal to x of t plus some step size times some direction, right? And so we saw gradient descent, and in gradient descent we saw that there were different ways of choosing the step size. We could either choose the step size to be a constant independent of t, or we could fix some particular function of t to be the step size. So for instance, you could have a large step size in the initial steps and then make that step size decrease as t becomes large. But then we could also use search methods for finding the best possible step size, and there are a number of different ways of doing this. Okay, and we saw a completely different approach, wherein you have not just first order information, but you also have second order information of the function at every point. So you have access to a zeroth order oracle, a first order oracle, and a second order oracle. You can compute the function, you can compute the gradient and the Hessian at every point. And using this, we derived the so-called Newton's method, wherein xt plus 1 is xt minus the Hessian inverse times the gradient of f of xt. So it's as though you took gradient descent and replace the step size, and of course it's not just the step size, but you also have some kind of a transformation. All right, so this is in general going to be some linear transformation. All right, so I'll talk a little bit about Newton's method and then also say something about the convergence of gradient descent for constant step sizes. In fact, we'll prove a rate of convergence result for constant step sizes. But before that, a couple of points. So this was something that one of your friends raised, which is, I said that if a function is discontinuous, then it cannot be convex. All right. There's a minor thing to be careful about. So it's okay, you can have convex functions which are discontinuous at the boundary of the domain. So for example, you can take the following function f of x, which is 1 if x is, so this function is defined only on the interval from 0 to 1. I can have f of x to be equal to 1 for x at the boundary points, and 0 which at all points which are not in the boundary. All right. This is convex. It's easy to convince yourself that this is convex. All right. But if the function is discontinuous at any point in the relative interior or in the interior of the domain, then this function cannot be convex. So in particular, if you have a function that is defined over all of R, then the function has to be continuous for it to be convex. Okay? Any questions? So in particular, if I have a function that is defined on some bounded set, and let us say that on the, so I take, so suppose that f from A to R, and suppose it takes some values in the interior. All right, so suppose that f from interior of A, so say that f is convex, convex in the interior of A, and you take any, and maybe also bounded, right? Now if I set f of x to be equal to any value other than y, so I have some convex function which is defined in some bounded region, all right? And suppose that the maximum value that the function can take is y, all right? At the boundary, I define the function value to be something more than y, constant, fixed, but more than y. Then the resulting, this function is also guaranteed to be convex. So less than it won't be, right? But any value that is more than y is okay. It will always be convex.
Shouldn't that z be something like a supremum for that function?
Which one?
That z. You can't just take z, any random z which satisfies greater than or equal to y, right?
So z is greater than supremum of f of x, right? Because y is greater than or equal to f of x for all x in the interior.
True. So what I'm trying to say is you could still have like a on the boundary a jump kind of thing, right?
Exactly, but
So
it's still convex.
acceptable.
That's acceptable.
Okay.
So that's the point that I'm trying to make. That as long as you have a jump at the boundary, and the jump it's a positive jump from the function, right? It's much more than any value that the function can take in the interior. Then the resulting function is still convex. So you can have a jump at the boundary and still be convex.
Basically like a well and its rim.
Exactly. So it's like a well, and at the rim you just pull it up as much as you want, it will still be convex. That's a good analogy. Any questions?
We're taking care, within that interior points, whether it is convex or
Within the interior, it has to be continuous. If it is discontinuous at any point, yeah, of course. So I'm assuming that f is continuous and convex in the interior. Otherwise, it doesn't make sense. Right? Anyway, it's not convex. The other point is regarding the convergence of these gradient or Newton's method, gradient-based methods or Newton's method. As you saw in your homework assignment, if you don't choose your step size carefully enough, then gradient descent can essentially diverge, right? But I think someone asked the following question is, can we prove that Newton's method is always guaranteed to converge if the function is convex, right? Or strictly convex. Suppose that f is strictly convex and I run Newton's method starting from an arbitrary point. Is it always guaranteed to eventually find the minimum? Right? It doesn't matter how long it takes to reach the minimum, but can we say that it's always guaranteed to find the minimum? Right? So let's do the following example. Okay, let's take f of x equal to half square root of 1 plus x square. And first stage, we need the first and second order derivatives. Let's compute those. What is the first derivative equal to? X by? Yeah, I mean to half, so it's x by square root of 1 plus x square. What? Sorry?
X by 2.
X by 2?
There should be 2 in the denominator. X is 1 by 2 x.
Okay, sorry, that's right. That's fine, right? So let me change this. Let me make this square root of 1 plus x square. Again, it doesn't change the example significantly, but just for the sake of this. Okay, so this is just x by square root of 1 plus x square. What about the second derivative? It's 1 by 1 plus x square equal to the power 3 by 2. Okay. So now let's see what happens in Newton's method. So what is xt plus 1 equal to? Xt minus the first derivative divided by the second derivative. So okay, so even before I get to that, what can you say about the function f? Is it convex? Is it strictly convex? Why? Exactly. So this is strictly greater than 0 for all x in R. So this is a strictly convex function. Okay, so this is xt. What is this equal to? This is xt minus xt divided by square root of 1 plus xt square times 1 plus xt to the power 3 by 2. So xt into should be square. Right? So this is minus xt cube. Right? So if I sort of plot the function f of x, it will look something like this, right? By the way, what is the minimum of f of x? Yeah, it's 1 and it's achieved at x equal to 0. Right? So suppose I start with an arbitrary xt, what happens? So I run Newton's method. I start with an arbitrary x0. Okay, x0 equal to something. Let's say x0 equal to 0.5. What would be my sequence of iterates?
If you start at 0.5, it will converge.
It will converge, yes.
Because less than 1, the cube will be smaller and smaller.
So if I start from any x0 which is less than 1, then this algorithm will converge. It converges pretty fast, right, at sort of a cubic rate. So, but at the same time, it's also alternating signs, right? So if I start with 0.5, if x0 is 0.5, or if x0 is positive, then x1 is going to be negative, x2 is going to be positive, and so on. Right? So if I start with any x0 which is less than 1, then I go to some other point here, and then some point here, some point here, and so on. Right? So it would keep switching signs, but eventually it would converge. It converges pretty fast. But what happens if I take xt greater than 1? Then again it oscillates, but then it diverges. Right? Jump here, and so on. Right? Basically, the step size is too much. So Newton's method is in general not guaranteed to converge even if your function is convex. So you have to be careful.
Here is the initial point, right? Not the step size.
Here is not the, yeah, correct. It's the initial point. So if the initial point is greater than 1, there's no step size, right, in Newton's method. So if the initial point x0 is too large, or in other words, it's too far away from the point of minimum, then Newton's method is not guaranteed to converge. But on the other hand, you can prove that if the initial point is sufficiently close to the point of minimum, then it converges fast. In fact, one can prove a quadratic rate of convergence. That is, yeah. So suppose that f is convex and x star, in fact, something even more. Even if you have a general function f and you're sufficiently close to a local minimum, right? And you start with an x0 which is suitably close to x star, which is a local minimum, and you have certain guarantees that for all points within this particular ball, the Hessian is not too large, sufficiently small, and for every pair of points, the Hessian doesn't deviate too much compared to the distance between those 2 points. Okay, so if you have these 2 conditions, then one can formally prove that x, in the first step, when you go from x0 to x1, right? So x1 is guaranteed to be closer right? So x1 is guaranteed to be closer to x star than x0, and by how much? This is exactly by this much. We saw something slightly stronger in the previous example. So if we start with x0, x1 is guaranteed to be, or x1 minus x star is equal to x, switching notation. So x1 minus x star is mod x naught cube, which is less than x naught square. So the only thing that Newton's method guarantees is that if you're reasonably close to the minimum, then you converge fast. But if you're far away from the minimum, then you can diverge.
How do you find the close enough the practicing?
Depends. So one way is to sort of try to run something like gradient descent, try to get somewhere close to the minimum, and then run Newton's method. Or you know something more about the problem. So the problem has enough structure where you're sort of guaranteed convergence. But there are other ways of improving Newton's method also. You sort of add a damping term. So the problem that happened over here was that,
You add another step.
yeah, so basically if x is greater than 1, then the second derivative is too large, which leads you to jump back and forth and you go too far away from the minimum. All right. So this quantity is too large. So instead of running xt plus 1 equal to xt minus this particular quantity, you run xt plus 1 equal to xt minus some delta t times this quantity, where the delta t is a damping term which guarantees that it's small enough. Right, so there are many other sort of ad hoc techniques, heuristic techniques that are used to improve Newton's method. Okay, so now let's try to analyze the behavior of gradient descent. Or how do you prove that, or how do you prove or derive a bound on the rate of convergence of gradient descent? For general functions, it's impossible to derive a bound on the rate of convergence. But now we can make some assumptions. That is, we'll assume that once again you're not too far away from the minimum, or in this case there's a parameter which tells you how far away from the minimum you are, and how long you take to converge depends on this parameter b. If you're far away from x star, then it will take you longer to converge, but if you're close enough, then hopefully you will converge faster. The second requirement that we'll need is that the gradient is always bounded. All right, and in fact, like some of these assumptions can be relaxed. So for instance, it's enough if this holds only in this particular region and so on. All right, within a ball of radius b around x star. But anyway, we'll make these two assumptions, that the gradient is bounded, the norm of the gradient is bounded, and your initial point is b far away from x star. And we'll assume that you know these parameters beforehand, or you at least have an upper bound on these parameters. But the nice feature about this analysis is that even if the function is not differentiable, the analysis still goes through. You just replace this by the subgradient. As long as the subgradient is bounded at every point, this exactly the same thing goes through. And again, the goal is we want to know how long it takes to get epsilon close to the minimum. And the claim is that you can get epsilon close to the minimum as long as the number of steps you take is greater than or equal to b square rho square by epsilon square. Okay. Except that there's a little difference in the algorithm itself. So note that this is not, the quantity over here is not xt, it is some x bar t. So I'll modify gradient descent in a little way, which is I run gradient descent for t steps. All right, I get I run gradient descent, I get x1, x2 up to xt, and in the end, instead of outputting xt, I'll output the average of all of these. Okay, so this is going to be the output of the algorithm. It is just that this makes it easier to analyze. So in practice, you will not do this. It is. So if this quantity is closer to the minimum, then xt would be closer to the minimum. Right? So it's enough to prove something about this. It's just a trick. I'm sorry?
Like if it overshoots,
Correct.
then the mean might be close to 0, but your xt would be far away.
The mean might be correct. But it doesn't matter. So I'm essentially going to prove that this is close to the minimum. There are other ways of proving that xt is to show that to show a similar bound on xt instead of x bar t. But at least for the purpose of this discussion, I'll use this just because some steps in the proof make it easier. Alright, so let's first look at f of x bar t. We want to show that this quantity is less than or equal to epsilon. Alright, with this is nothing but f of 1 by t right. Now I know that the function f is convex. That's what we assume. So what can you say about what kind of a quantity is this inside? Yeah?
Convex combination.
So the term inside is a convex combination of the xt's. So let me use the definition of convexity. So this is less than or equal to 1 by t, summation t equal to 1 to capital T, f of xt minus f of x star. But I can just write this as 1 by t summation t equal to 1 to capital T, f of xt minus f of x star. Okay. So right away, hopefully, even if f of xt minus f of x star, if this is bounded, then you can immediately see that as t becomes large, the right-hand side becomes small. Right, so we already have some reasonable control over f of x bar minus f of x star. Okay, now we know that f is differentiable. What can you say about f of xt minus f of x star? So let me use the following. Okay, so my claim is that this quantity is again less than or equal to t equal to 1 to capital T, the inner product between the gradient of f at xt and xt minus x star. Why is this true? Yeah, so what property did I use? Which directional derivative? Yeah, but how did I get from f of xt minus f of x star to this? In a sense, right? Correct. So we use that first order property of convexity, which basically tells you that f of xt is I think I should. I think I wanted f of x star is always greater than or equal to f of xt minus gradient f of xt times xt minus x star minus xt. I'm sorry, correct. Plus f of xt times x star minus xt. So f of xt minus f of x star is less than or equal to gradient f of xt, whatever, dot product, this should have been a transpose xt minus x star. Right, I just moved this to this side and moved this here. Okay, so now I claim that now I have some bound over here as 1 by t times summation of the inner product of the gradient at xt along with dot product with xt minus x star. I claim that this is less than or equal to one by t times norm x 0 minus x star square by 2 delta, where delta is the step size that I used for my gradient descent method, plus delta by 2 summation t equal to 1 to capital T norm gradient of f of xt square. Okay, so this claim is something that I still have to prove, but let's suppose that the claim is true. What did I assume on this first quantity? about this first term.
Within B.
Yeah, it's less than or equal to b. And what about the second term, f of xt? This quantity is less than or equal to rho. Right? So if I use these two, I get that this is less than or equal to 1 by t times b square by 2 delta plus delta by 2 times t times rho square. So this bound is true irrespective of what delta I choose. So but instead if I choose delta to be equal to b divided by rho times square root of t, then this is less than or equal to, this is equal to b square divided by 2b rho square root of t plus b divided by 2 rho square root of t times rho square. This rho and this rho cancel. This b and this b cancel. I also have square root of t. So I have b times rho times square root of t divided by 2. This eventually just becomes b times rho times square root of t. So f of x bar t minus f of x star is guaranteed to be less than or equal to b times rho times square root of t. So if I set this to be equal to epsilon, if I want to, that's my target, that I want to get epsilon close to the minimum, then this would require t to be greater than or equal to b square rho square divided by epsilon square. Okay, is that okay? So in fact, a slightly different set of assumptions and different analysis. So if we assume that gradient f of x minus gradient f of x prime is less than or equal to L times norm x minus x prime. Then you can in fact show that t equal to some constant times L b square by epsilon, time steps are enough. The crucial point here is the dependence on epsilons. Here I have an epsilon square, here I have an epsilon. And that can sometimes make a very big difference. Because here there's a huge blow up in epsilon. But essentially both these correspond to the same algorithm. Alright? It is just a different, it depends on how regular your function is. Alright, so in this case we are making a different set of assumptions on the function. In the previous case we just assumed that the gradient is bounded. But no matter what you do, you can't really improve the dependence on epsilon in gradient descent. On the other hand, under again some mild conditions, we can prove that any algorithm must take at least some constant times 1 by square root of epsilon time, where the hidden constants may include whatever these terms like B and L and so on, but the dependence on epsilon has to be at least like 1 by square root of epsilon. You can't improve. No algorithm can do any better than something divided by square root of epsilon. So basically this is the number of steps it requires you to get epsilon close to the minimum. So it's possible to prove lower bounds on any algorithm. The best algorithm that you can ever possibly hope to design must take these many steps or this much time to get epsilon close to the minimum. For arbitrary functions, for specific functions, sure, it can converge much faster. But for the worst case function, for that algorithm, the time required would be something divided by square root of epsilon. And in fact, there is an algorithm that gets you to something divided by square root of epsilon. And hopefully if there's time, I'll try to cover that. It's an acceleration method for gradient descent. It's again a gradient descent type algorithm, and something that was discovered fairly recently, maybe in the last couple of decades or so. That's what I mean when I say recent. All right. But it's a nice algorithm, and hopefully if we have time, I'll at least tell you what the algorithm is. Sorry? You use some regularity assumptions. So okay. If you look at the book by one of the reference books, the book by Nishit Vishnoy, there's a proof that is given which doesn't, which makes certain assumptions. That is, if t is less than the dimension of the search space. So if suppose you have a function f from Rn to R, and you run gradient descent for something that's at most a constant times n number of steps, where that constant is less than 1. Okay, then you can prove a lower bound of this form, and the way it is proved is one high level idea is that suppose that you run it for t time steps, then xt can basically be in some t dimensional subspace starting from the initial point. Because at every point, so if you think about xt in terms of x0, what is it? It is x0 minus something times the gradient, that is x1, right? x1 minus something times the gradient is x2. So x2 is x0 minus some gradient plus something times a gradient plus something times another gradient, right, and so on. So xt is nothing but x0 plus one gradient vector, some plus a linear combination of t gradient vectors. All right. So in
Gradient, in each iteration you can sort of reduce one dimension.
correct.
So, why can't you do more than one dimension?
Because it's just you know that in t time steps, so xt is x0 minus something. So this is basically delta times or whatever delta 1 delta 0 gradient f of x0 minus delta 1 gradient f of x1 minus delta 2 times gradient f of x2 and so on, right? So this whole thing is a linear combination of t vectors, right? So xt can basically lie in some t dimensional subspace that includes x0, right? And that's one sort of key idea behind the proof. So basically this restricts how far you can be from x0. And then you can try to design a function for which you require at least a certain number of, so you're at least something far away from any given x0. All right. Remember, when again, this particular statement, there's a lot more involved in this particular statement. I just stated this very loosely. So basically, we want this to happen. What is the time that is required for every function and for every x0 satisfying certain assumptions? Suppose that x0 is within b distance to x star, and for the worst case function possible. How long would it take to get epsilon close to the minimum? Okay. Again, there's a lot more involved. I'm not going to cover the proof over here, but that's sort of the very high level intuition about what can be done, about what can't be done. Okay, so in the time that I have left, okay. All right, so now we have a bound on the performance of gradient descent, assuming that this claim is true, right? And in fact, I'll prove this in a little more generality. In fact, it will hold not just for gradient descent, but essentially any descent-based algorithm. So in fact, I'll assume, let's consider a general algorithm which takes the form xt plus 1 equals xt minus some delta vt minus 1. So constant step size, but you can choose the directions any way you want. Now in this case, let us look at inner product between Vt and xt minus x star. Because this was exactly the quantity that we had back here, right? Right, this was the quantity that we wanted to bound. So let's look at one term that looks like this, which is just Vt, inner product between Vt and xt minus x star. So I can write this as 1 over delta times inner product between delta times Vt and xt minus x star. Just from the linearity property of the inner product. What I'll do now is try to sort of make the right hand side look like a square or a difference between squares. So I can write this as 1 over delta times norm of delta Vt minus xt plus x star square minus this particular quantity plus norm xt minus x star square plus delta Vt square. Right, I'm just using the fact that 8, okay, so there should be a 1 by 2 over here. Basically, a times b is equal to a square plus b square minus a minus b the whole square. That's all. So this, if I
Should this not have a norm B, norm x minus x star, norm?
where
If that's what you're using, because that is actually a b cos theta, right? You're in a product.
correct. So
then
basically
cos theta norm.
norm x1 minus x2 square is basically norm x1 square plus norm x2 square minus 2 times the inner product between x1 and x2. Right?
This is the cosine rule.
Yeah, this is the cosine term. That's exactly what I've done. Just rearrange. Okay, so I have this. I basically want to rewrite this in the following way. So this is x star or I want to write this as xt minus delta Vt minus x star square. Right? Because norm x square is the same as norm of minus x square. But what can you say about this particular quantity here? Or more importantly, this quantity here. What is this? That is xt plus 1. So this is equal to 1 by 2 delta times minus norm x t plus 1 minus x star square plus xt minus x star square plus delta square times norm Vt square. So let me take 1 by t times summation t equal to 1 to capital T Vt xt minus x star. Right? What can I say about this quantity? Yeah?
You'll get chain cancel and only the last term first.
Correct. So it's basically a telescoping sum. So everything except the first term and last term just gets cancelled out. So this is equal to 1 by 2 delta times norm x, whatever, x1 minus, okay, perhaps I should have, that's okay. Maybe I should have done this from t equal to 0 to capital T, t minus 1. So this is x0 minus x star square minus x capital T plus 1 minus x star square plus delta by 2 norm Vt square. Right? The second term here is something that is non-positive, right? Including the minus sign, of course. So this is less than or equal to 1 by 2 delta norm x0 minus x star square plus delta by 2 summation t equal to 1 to capital T norm Vt square. And this is exactly what we claimed. Basically it is 1 by 2 delta norm x0 minus x star square plus delta by 2 summation t equal to 1 to capital T gradient f of xt square. Any questions? So far we've seen algorithms for unconstrained minimization of convex functions. At least we know something, what we can do. All right. If you're given an unconstrained minimization problem, the form minimize some f of x where f is convex, and you're able to find, let's say, the gradient or the subgradient, you can run the gradient descent algorithm with whatever choices of step sizes and try to arrive at an approximate solution. But these don't work if you have constraints. Right? Ultimately, all of these gradient descent or Newton's method, the main idea was to use the first order necessary condition. All of these gradient based methods, what they try to do is try to find a particular x for which the gradient of f is equal to 0. Right? That's what it ultimately boils down to. But this works if the minimizer is in fact an interior point of your constraint set. Right? But note that when you have a set of constraints, the global minimum of the function, of the unconstrained minimum, may not be equal to the constrained minimum. Right? In that case, what do you do? Right. So from the next class onwards, we'll try to explore various approaches to do constrained minimization. Right? So first, we'll try to develop a theory of trying to understand how do you even come up with constrained optimal solutions. And the high-level idea will be the following: that yeah.
Does this also work for if omega is a convex lattice?
Here we didn't have any notion of a constraint at all, right?
Like even if we have a constraint
Okay.
that makes the set convex.
So again, how do you impose the constraint for gradient descent? So in gradient descent, your xt plus 1, just because xt lies in the constraint set doesn't mean that xt plus 1 will also lie in the constraint set. Correct?
But you will sort of stop at the bound.
True. So one other approach is this so-called projected gradient descent. So basically, you start with an x0, which satisfies your set of constraints, and then you run for each t. You run the following. So you take an x tilde t plus 1 is equal to xt minus, maybe you run something like gradient descent, so delta t times gradient of f at xt. So this is the gradient, the descent step, and then next you run a projection step. So you set xt plus 1 equal to the argmin x within your constraint set k. So basically you first run one step of gradient descent, and then if you're inside the constraint set, well and good. If you're outside the constraint set, then you find the closest point within the constraint set to x tilde t plus 1.
How do you do it?
That's the whole game, right? If this were easy, then we didn't have to proceed any further, right? But this itself involves solving an optimization problem. It's a constraint optimization problem in itself, right? But the nice thing is that in this case, this is a constraint optimization problem where the objective function is fixed. It's a quadratic. So in many cases, there are separate algorithms that have been designed for, instead of this is probably easier to work with, the L2 norm square. All right. For several classes of constraint sets, this can be solved fairly efficiently. For example, if your constraints are all quadratic, then this results in what is called a quadratically constrained quadratic program. There are algorithms which you can solve, which you can use. I mean, the whole point is that you originally had a problem where you wanted to minimize some weird convex function over a convex set. But now I have somehow reduced this to minimizing a quadratic function, but with the same set of constraints. And hopefully this is easier to solve. If you know how to do this computationally efficiently, then you're done. If not, well, you need to think about something else, some other approach. But this is definitely easier than the problem that you set out to solve initially. Because the function, you know what the function is like. It's always quadratic. And for certain types of sets, this can be done. There are already well-known algorithms to do this.
You would have to do this every step.
Every step, yes. So in particular, when, for example, the set K is defined by linear constraints, there are sort of very easy ways to do this. Any questions? Okay, so maybe let's stop here.